Welcome back once again to another exciting episode of Dave Does Math from Home. Today we're going to talk about section 5.5. This is integration by substitution. I would like for us to be able to dive directly into some really cool applications for integrals so that we can see some of the really cool stuff you can do with those. We can't. The process of integrating functions gets really complex really fast. And a lot of the applications I want to do involve us doing some pretty complex integrals. So we can't go straight into that. We're going to need to talk about an integration technique first. This technique will let us handle some of the more complex integrals you'll encounter in Calc 2. And once we have this done, then we can go into the applications and see what kind of cool stuff we can come up with. So integration by substitution is sort of like the antiderivative version of the chain rule. So let's do a little bit of review so that comment makes sense in context. When we did derivatives, we decided that addition, subtraction, and coefficients are safe. If these things appear in your function, you don't have to do any weird special fancy nonsense to take derivatives of them. They behave like you would expect them to while taking a derivative. They're safe. They're nice. Multiplication, division, and composition are unsafe. If you were trying to take the derivative of a function that was a product of two other functions, or a function that was the quotient of two other functions, or a function that was a composition of two other functions, then things got messy. We could do it, we just had to involve extra steps. When we were doing derivatives of products, we had to use the product rule. Derivative of the first times the second plus the derivative of the second times the first. I can write it much more easily than I can say it. For division, we had the quotient rule, which was the top prime times the bottom minus the bottom prime times the top, all divided by the bottom squared. Hopefully that's coming back to you. If not, review that. You'll need it. And then composition. For composition, we had something called the chain rule. When we were taking derivatives. And that's how we took the derivatives of things that looked like they had an inside and an outside. So, for integrals, we have the same sort of structure. Addition, subtraction, and coefficients are safe. Multiplication and division and composition are unsafe. We need special rules to be able to do antiderivatives for functions that are products or quotients or composites. And the antiderivative version of this, it's not the chain rule, it's called integration by substitution. But it's very similar to the chain rule. It's like doing the chain rule backwards. So, this is the quick breakdown of what's safe and what's not in integral land. It matches what's safe and what's not in derivative land. The thing that's going to be different are the rules we use. Here we have product rule, quotient rule, chain rule for derivatives. For integrals, when we have products, we're going to have to do something called integration by parts. When we have composition, we'll have to do this, integration by substitution. And when we have division, it's probably best to change the division instead of having a over b and trying to work with a division, it's probably best to do a times b to the negative 1 and do some sort of product times a composite. There's no nice rule for divisions. You just got to use products and composites together. So that's the structure of what we're going to get into. Let's get into it. Quick review of the chain rule. If we have a function like f of x equals sine to the 5th x, we can identify the inside function as sine of x, and its derivative is cosine. We can identify the outside function as something to the 5th power. The derivative of that is 5 somethings to the 4th power. And of course, my mantra throughout all of these problems is the blob never changes. So whatever this blob is, this is that same blob. It's not a different blob, it's the same blob. So if this is sine of x, this also has to be sine of x. That means that the derivative of the whole thing is the product of these pieces. 5 sine to the 4th x, that's 5 blobs to the 4th, times cosine x. That's the chain rule, and that is how we do it for derivatives. So let's look at some antiderivatives. Let's talk about the antiderivative of sine to the 4th x cosine x dx. Hopefully, this is extremely simple. The antiderivative of 5 sine to the 4th x times cosine x should be sine to the 5th x plus c. I know this because we just did that here. If the derivative of sine to the 5th x is 5 sine to the 4th times cosine, then the antiderivative of 5 sine to the 4th cosine should be sine to the 5th. We're going to talk about the mechanics of this and how to do this without first doing a derivative. But before we get into that, I kind of want to start to address the question, where did the cosine go? And my answer to that is, where did it come from? The disappearance of the cosine in the correct antiderivative of this function is a source of much confusion for students when they're first learning this topic. And so that's why we're addressing that first. Lots of students will look at this and think, oh, okay, so the antiderivative of sine is cosine, and the antiderivative of something to the 4th is something to the 5th. So they'll think of this as some kind of cosine to the 5th, and then they'll try to do an antiderivative of this separately. And none of that works, actually. None of that works at all, because function composition isn't safe, function multiplication isn't safe. And both of those things are happening here. This is a composite function, sine of x to the 4th power. That's a function inside of another function. And it's a product as well. So this is composition and a product in the same integral, in the same antiderivative. Neither of those things are safe. And yet the answer is very clean, very simple, if you know where it came from. Where it came from introduces a cosine as a product to this piece because of the chain rule. When you're doing derivatives with the chain rule, you add pieces into it. For every layer of composition, you get a new link in your chain that attaches itself to the end of your function. So you're adding pieces when you do the chain rule. So it makes sense that when you're doing the backwards chain rule, some of these pieces are going to disappear. You have a cosine here, no cosines here. They go away with an antiderivative is sort of the best way I can put this. Hopefully, looking at sort of the mechanics of how this happens will clear up some questions that you might have. And we'll do plenty of examples of these, so don't worry about that. My suggestion for actually doing this process in an antiderivative sense is to start the same way that we did chain rules. In Calc 1, when we did chain rules, the first step was to identify the inside and the outside and take derivatives of them. That's always the first step here. When you're doing integration by substitution, I think that you need to start in the same way. You need to identify all of the pieces that you have in your function. Except this time, instead of an inside and outside, there's going to be 3 pieces. The inside function is sine of x. That hasn't changed. The outside function should be 5 somethings to the 4th. And then in this case we have an other. The other function is everything else. So the inside and the outside is composite, the composite piece. And then everything else you have in your function is the other. So it's the whole thing. Cosine of x dx. The whole piece is the other function. Here's another source of confusion that I'd like to head off right away. Lots of people, when they first see this sort of setup, they tend to think that the cosine should be the outside function because it's the thing that's separate and like outside of this mess. That's not what outside means. Inside and outside are the 2 pieces of the composite function, and the other is the one that's completely separate from all of that. So these are our 3 pieces: inside, outside, other. This is every piece of this integral is now accounted for. So to proceed, we're going to set w equal to the inside. We're going to set w equal to the sine of x. And then we're going to find dw. Remember from Calc 1 that d something means the derivative of that thing. So dw, and think about this dw in terms of like implicit differentiation sort of stuff, or related rate stuff. When we had these, every time you took the derivative of something, you added a d to it, that sort of thing. So if w is the sine of x, then dw should be the derivative of sine of x dx. This is dw. We are introducing this variable and its derivative so that we can, I erased it, dang it. This whole section is called integration by substitution. So the reason we're introducing these variables is so that we can do a substitution. And what we have right now is the inside function equals w. So I can just replace that whole thing with w and have a w here. dw is a perfect match for the other function. So I can replace this whole thing with dw. I'm going to erase the top bit because I don't think that's necessary anymore and I need some space. But once you have this connection set up, you can rewrite this as this equals the integral. The outside function doesn't change, but I'm replacing this bit with w. So the integral of 5w to the 4th, that's this, 5w to the 4th, and this whole thing is dw. That's where the cosine goes in that question I was trying to answer earlier. Cosine becomes part of the derivative of the inside function, which, when we integrate this with respect to w, this is very clearly just w to the fifth, plus c. So if we swap out our sines and cosines for w's and dw's, this integral gets really easy. And we can just do w to the fifth there. And then we just have to unsubstitute. W was the sine of x, so this is sine to the fifth x plus c. And that's it. That's the whole thing. That is the correct answer that we knew we were going to get to. So the cosine and the dx both get sucked into a new dw that serves as sort of like the end to this integral sign. That's where it goes. Hopefully that is pretty clear. We're at about 16 minutes, so I'm going to cut this video here, and I'm going to do a bunch more videos with a bunch more examples. So stay tuned.